let me log you out of here. Okay, now there were some questions on homework. Now I lent my book out to someone, so I don't have a book. So if you have a question on a homework problem, I'm going to need to look at someone's text. I know over here we had one, right? Did you have one? Which one was it? Number 28 for the derivative. Okay, so if it's 28, it's this one. Y equals arctangent of the square root of, is this looking right? 1 minus x over 1 plus x? Okay. Who else asked me about question? Who else? Which one was yours? 39, the 10-foot ladder? Okay, I'll get back to that in a second. Here you go. All right, so for this one, we want the derivative. So remember from last class, if y is equal to arctangent, I'll say of u instead of x. U is more general. We use that when we're trying to apply like chain rule. The derivative of this, what's the derivative of arctangent? 1 over 1 plus x squared. In this case, I would say u squared, right? And then you would always have to multiply times, because of chain rule, the derivative of whatever u was. Usually we just put u prime or du here. If that's an x, then the derivative of x there is always just a 1, so we don't usually put it. But that's the formula I'll use for this. For us, the u is this big thing right here, right? It's that entire thing. So we're going to go, derivative of this is 1 over 1 plus, now when you square that whole thing, you get 1 minus x over 1 plus x, because when you square it, the square root goes away, right? Then we have times, chain rule, the derivative of what's here. And that's going to require chain rule. We have square root of something, we need to take derivative of that, and then we have to do the derivative of what's inside, which would be a quotient rule, wouldn't it? So we have to kind of do that all at one time. I'll go a little slower here. I'll do this in blue. If I have the square root of 1 minus x over 1 plus x, and I take the derivative, it's going to be 1/2, then all of that, 1 minus x over 1 plus x to the what? Negative 1/2. And remember last class we talked about some students, they were comfortable doing it that way. The other students were writing 1 over 2 times the square root. Okay, either way, you should still get to the same place. That's the derivative of the square root of something. Now the derivative of what's inside. So now we're going to do quotient rule. How many of you learned quotient rule with that little saying, high-de low, low-de high? Anyone learn that one? Okay. Do you use that one? You use it? Yeah? Okay. If you haven't heard that, is it high-de low, low-de high? Low-de high? Okay. Low-de high. Low, derivative of high. Low-de high minus high-de low. High, the top one, times the derivative d of the low one. I don't know if that makes any sense to you. I just always remember it as, you know, just a formula. I think if you've done it enough, it's just there, right? Derivative of this would be derivative of the top, which is negative 1, times the bottom, 1 plus x, minus, you can either say derivative of bottom times the top, or you can say the top times the derivative of the bottom. However you learned it, 1 times 1 minus x, which will be 1 minus x. All of that divided by 1 plus x, quantity squared. Now, was your question in the derivative, or was your question in the simplification of it? The simplification of it. All right. Okay, well, it's not necessarily wrong. This problem can go lots of ways. So let me go back here. 1 over 1 plus 1 minus x, or 1 plus x times, we have the 1/2 times, I'm going to say, if you have a fraction to a negative power, what can you do to change that to a positive? You could flip the fraction, right? Reciprocate the fraction. So I could say, if I wanted to, this is 1 plus x to the 1/2 over 1 minus x to the 1/2. So what I did is I flipped the fraction, which made it a positive 1/2, and then I applied the 1/2 to both the top and bottom, which is a completely legitimate move. And then I'm going to simplify everything in here. So I think, pardon me? -2, and the x's cancel out. So you just get -2 up there. On the bottom, 1 plus x squared. Still good? Any questions? I see that since these two are the same, base, I can mess with these exponents. That'll really turn into a 1 plus x to what power on the bottom? How do you put these two? What cancels? Y'all following me here? Three halves on the bottom. 1 plus x is 3 halves on the bottom. I'm looking at you to see if you're following that, or if I really need to show that. Okay, let me come back to it. I'm just going to leave it in red for a second. How about this 2 and this -2? That's good, right? Okay, that's -1. Before I cancel the red ones, let me try and work with this a little bit. This is what we call a complex fraction, right? It's a fraction with fractions. So to do this, I'm going to try and clear out this fraction. So I'm going to multiply by 1 plus x here, which means I have to multiply 1 plus x here and 1 plus x up here. So multiply 1 plus x across the top and the bottom. If I do that, I get 1 plus x on the top. On the bottom, the 1 plus x multiplied times that 1, it gave me 1 plus x. Then it multiplied times this, which gave me plus 1 minus x. I still had over here, I'm just going to pull that -1 that we got way out. I'm going to put the 1 plus x to the 1/2 over 1 plus x to the 2, and then times 1 minus x to the 1/2. All I'm doing is just algebraically moving things around. I put these two together, moved that one out to the side, brought the -1 out here. This is this. Do you see the 1 plus x here and the 1 plus x here, right? What does this turn into down here? Bottom there is 2. 2, right? So that's good. This one right here is 1 plus x to the 1 power, isn't it? See, the reason why I didn't cancel this yet, because we were talking about it and people seemed like, what? It seemed like when I was asking, people were like, what's going to happen there? The reason why I didn't cancel and I said wait is because I realized after looking at it that when I did this, it was going to come up with one of these up here. But that's just after, years and years of doing this. I see that. That's not necessarily something you would have seen right away. But algebraically, it's still all the same. We're just doing algebra here. How about these two together? Can we put those together? It's 1 plus x to 1 what power? 3 halves. Okay. We said this turns into a 2. So I have a -1/2 out front. I have that 1 plus x to the, we said 3 halves. On the bottom, we had what? 1 plus x to the 1/2? Oh, wait, no, squared. Yeah, sorry. Oh, no, I'm looking at this one right here. So it's squared. Thank you. And then times this one right here. So 1 over 1 minus x to the 1/2. Jeez. All right. What happens here? That's a 3/2 up here. You subtract, right? 3/2 take away 2 leaves you with -1/2. No. Yes? No. -1/2. Then we're going to drop it back down and make it 1/2 on the bottom. So we have -1/2, 1/1 plus x to the 1/2 times 1/1 minus x to the 1/2. But since these both have 1/2 on them, I can put them together, right? Yes? So I could say this is -1/2 times 1/. Isn't the 1/2 the square root? Okay, so I could say square root, and then I put those together, right? Which means I can multiply them, and aren't they a difference of squares? So it becomes 1 minus x squared. I don't know if that's what the book has. Is that, are you trying to match it to the book, or? Okay. Is that what they got? That's what. Okay. Are you okay now with it? Yes? Okay, good. Good question. From here? Okay. Okay. All right. Now, the other question was the 10-foot ladder problem, right? All right. So can I see your book one more time? Okay, this is number 39. It's a word problem, so I'm not going to write it all down. I'll just state what it said. A ladder 10 foot long leans against a vertical wall. So I'm going to start drawing because I haven't actually done this problem. So let me. 10-foot ladder, wall. If the bottom of the ladder slides away from the base of the wall at a speed of 2 feet per second, so the bottom of the ladder, this point right here, is moving this way at 2 feet per second. By the way, that ladder was 10 feet long. I'm paying attention to that because my units have to match, right? If they said the ladder was 10 meters long and it was moving 2 feet per second, we would have to convert everything to meters or feet. So always making sure we're paying attention to that. How fast is the angle between the ladder and the wall changing? Where's that in my picture? Angle between the ladder and the wall. It's this one right here? Ladder and the wall. This one. How fast is that angle changing at exactly the moment when the bottom of the ladder is 6 feet from the base of the wall? Thank you. That means we're talking about this point is 6 feet from this, right? Okay, but remember last time we talked about drawing two pictures. One picture is what's happening as things are changing. The other picture is what's happening at the exact moment in time. At the exact moment in time, this is 10, this is 6, right? And of course, then I can always find this side of the triangle. In the general picture, this side's moving, changing, this angle's changing, the 10-foot ladder never changes. So what I need to do is come up in my general picture with some variable label for this side. So how about x? Is that okay? No? Questions? I'm trying to find what here? D theta dt, right? I'm trying to find the rate at which the angle is changing. I labeled the angle theta, so I want d theta dt. I'm given in the problem that what's happening? The ladder's moving at the bottom of the ladder, this point, is moving 2 feet per second. That means the x is changing that fast, right? So dx dt is given to me to be 2. I said last class, I'm not real big on carrying my units. I just do it, and then at the end I look at, you know, what I'm trying to put a quantity on, and just kind of reason out what the variables are. When exactly is it that we want this? Okay, so we want this right here. We want to find d theta dt when x is 6 feet, and we're ready to go. So we just have to find a relationship between theta and x. Sine function? Sine is opposite over hypotenuse. So if you turn your head opposite hypotenuse, so we can use sine. So using the relationship here that sine theta is opposite x over hypotenuse 10, I now have an equation that I can differentiate with respect to time. Now the reason this appears in this section is because they really want you to use the inverse sign here to get theta by itself. That way when you take the derivative, you'll have d theta dt right away without having to mess around with pulling it out of stuff. So before I differentiate, I'm going to take arc sine on both sides of the equation. Arc sine on the left side of this wipes out the sign, right? Cancellation property. Right side, we get this. I move the 1/10 out in front of the x because as calculus students, we always like our constants in front, don't we? At least I do. All right. Now I'm ready to take the derivative. So I'm going to do implicit differentiation, derivative with respect to time on the left side, d theta dt. Right side, we've got some chain rule, right? What is the derivative of arc sine of something? 1 over the square root of 1 minus whatever was in there, right? Squared. So can I say 1/100th x squared? Is that fair? But then chain rule says I now need to go in here, take derivative of what was inside. What's the derivative of 1/10 x? 1/10. 1/10. And the great thing about the formula looking like this, bless you, is that if we're given x, right, which we were, we can just plug it in now and we have d theta dt. We're not going to have to move things around and try and isolate things. I mean, we're ready to go. So just plug in 6 now. Oh, thank you. Why didn't we say that before? I said, what's the derivative of 1/10 x? We didn't say 1/10 dx dt. Obviously, we have to have that because it's moving. So plug in our 6, plug in our 2, right? And we're done. Does that clarify? Who asked that again? I'm sorry. Right there. Thank you, sir. Are we good? Did I address the question then? What would our answer be in units? What would the units of our answer be? Angle is measured in this problem. Well, they don't tell us, so we just say radians per, and time here is seconds throughout the problem. It was a second, so radians per second. And they don't specify in the problem how they want the answer, right? They just say, yeah, so it doesn't say like in degrees per hour or degrees per minute. So we just put it radians per second is fine. All right, good. Now, anything else? No? We are at 3.6, right? We finished the 3.5, so we're going to start with, were you raising your hand, sir? No? Who? Someone rose there. I thought I saw a hand go up here, no? We finished 3.5, so we're going to do 3.6. We're actually going to get through 3.6 pretty quickly today, and we're going to start the next section. Now, I don't have the notes online yet for anything after 4.7, but they will start appearing. I'm making them as I go, all right? So just keep your eyes open on Canvas for those notes to appear. All right, there are 6 additional trig functions which come from special combinations of e to the x and e to the negative x. They are called the hyperbolic trig functions, and they are defined as follows. So we have what we call the hyperbolic sine function. Now you can say sine hyperbolic, that's okay. Hyperbolic sine is the way most people say it, but you can say, if you're reading this, if you want to say sine hyperbolic, everyone understands what you're getting at. But the function is defined to be this. So don't think of the hyperbolic sine as like opposite over hypotenuse on a triangle. That's not necessarily what it is, all right? It is just some combination, some linear combination of exponential functions. It's e to the x minus e to the negative x divided by 2. That's it. That's its definition. And then we have cosine hyperbolic, which is almost the same thing as this, except what? Plus sine. And then the remaining 4 trig functions are just our standard ways of defining tan and cosecant and secant cotangent. So hyperbolic tangent is just hyperbolic sine divided by hyperbolic cosine. So you would take that entire expression, you would divide it by that expression, which means you would reciprocate things and cancel things, and that would be your tangent hyperbolic. But it, again, is some combination of those exponential functions. And then cosecant hyperbolic, that's 1 over sine, so it's just that flipped over, right? The sine hyperbolic, just flip it. That's this. Secant hyperbolic, take this one, flip it. And then cotangent hyperbolic, you just flip over the tangent hyperbolic. All right, so those are the 6 new functions. And here they are graphed. So this is what the hyperbolic sine looks like. This is what hyperbolic cosine looks like. I'll do it that way. Here's hyperbolic tangent. Kind of looks like cotangent a little bit, or arctangent. There's your cosecant hyperbolic. There's your secant hyperbolic. Cotangent hyperbolic. So those don't look anything like the sine, cosine, inverse cosine, right? They're like their own animals here. Now, the one that is probably the most interesting to us is this one right here, this hyperbolic cosine, because as we'll see at the end of the notes, we use this function to describe, if you take a wire, this one's it's not heavy enough, but if you take a wire and you hang it between 2 poles, the shape of that wire is not a parabola, so it's not a quadratic function. It's actually a hyperbolic cosine. So you know, when you look at utility poles and you got wires between them, right? That shape of that wire is some combination or some version of a hyperbolic cosine called catenaries. So again, we're in calculus, so we've established what those trig functions are, those hyperbolic ones, and we're interested in what their derivatives are, so we can get instantaneous rates of change and things like that. And remember last class I said one of the things that we would want to do is we would want to, in Cal 2, be able to measure like arc length. So, you know, if I'm going to be building a 400-mile power line connecting 2 major cities, and I'll probably, well, I don't know if they go underground or not, but, you know, if I'm going to be hanging wire, I'm going to need to know how much wire that is, right? Because I'm going to have to multiply it by however many thousands of sections I'm going to have, and it'd be nice to know what that length is, right? So you got to be able to measure that. So to measure it, you get its arc length, and do that, you do some calculus, right? All right, so here's the derivative of sine hyperbolic x is cosine hyperbolic x. Doesn't that look exactly like sine and cosine? I mean, that's what happened with regular old sine. Derivative of the sine of x was cosine x. So nothing's changed there. We're happy. How about this one? Derivative cosine hyperbolic or hyperbolic cosine of x is sine hyperbolic x. Does that look like what we had before too? Similar, right? But remember with cosine it was negative sign, wasn't it? So we don't get that here. How about this one? Is that like it was with sine and cosine? Yes. The derivative of tangent x was secant squared x, and here it's secant hyperbolic squared x. So that's the same. And these are similar also, aren't they? That's right. In the regular secant, yep, it's just secant x tangent x. Here it's negative. All right, so now we have the derivatives. Now I'm not going to show you. I don't think I'm going to show you. No, I'm not going to show you. But how could, I don't know, do you want to see why? I mean, it doesn't take a whole lot to convince yourself that this is this. All you have to do is take the derivative of this right here, right? Take derivative of that. So I'll do it because it doesn't really take a whole lot. If I take e to the x, and the sign is what? Plus, minus? Plus e to the negative x over 2. That's my sine hyperbolic, right? If I take its derivative, I'm going to first just rewrite it. That's the same thing, isn't it? I just took this, split it into two fractions, put it as a 1/2 out in front instead. And now take the derivative. What's the derivative of e to the x? Itself, right? So I get 1/2 e to the x. Now, what's the derivative of e to the negative x? Itself, but then chain rule says times derivative of what's up here. So -1 would pop out of there also. And that -1 would come out here in front of the negative, or in front of the 1/2 and make it -1/2. So we get -1/2 e to the negative x. And that is exactly the definition of cosine hyperbolic. Right? The only difference between sine hyperbolic and cosine was that negative here. You follow? Now you could do the same thing for all the others, but I'm not going to. All right, now once we've established what the derivatives of those are, we can start working some examples. So example 2, if y is this, let's find its derivative. Did I skip example 1? Oh, whoa. Wow. Okay, hold on. Something happened. I went way past some stuff, didn't I? Right here. Yeah, but I missed all the damn identities. Back it up. Something happened. My page break didn't work, so I thought this was the end of the page right there. All right. Sorry about that. We were supposed to do this before we did derivatives. So you're going to have to, don't just forget what I told you, but just hold off on that for a second. Here I showed you all the graphs, right? And now here are some very important properties or identities when it comes to hyperbolic trig functions. Remember the major identities that we had for pre-cal, right? What was one of the most fundamental identities with trig function? What we call that Pythagorean identity, right? Sine squared u plus cosine squared u is 1. Well, with the hyperbolics, we have something similar. Do you see it? If it was plus, it would be exactly like it was with pre-cal, but it's a minus and it's cosine in front of the sine. So I want us to show that this is true. All right? Let's just show that this is 1. I'm trying to show that cosine hyperbolic squared x minus sine hyperbolic squared x is 1. So if we're trying to show something is true, right? If we're trying to show that this is an identity, the way that you do things like this is you start with one side and you turn it into the other side. You are not allowed to work with this like an equation. You can't say, okay, I'm going to move that to the other side, because that's not, you don't know this is true yet. You're trying to show it's true. So I'm going to start with my left-hand side. I'm going to try and turn it into 1. Okay? Well, what is the definition of cosine hyperbolic? E to the x minus e to the negative x over 2. And then that's supposed to be squared. Now, minus sine hyperbolic e to the x plus e to the negative x, all of that over 2, all of that squared. So that's just purely the definition. Oh, yep. Thank you. It's one of those days, I can tell. It's Thursday. I'm already thinking about the weekend, I guess. Plus here, minus here, because that's sine, that's cosine. Now, at this point, what should I do? How about just square them? Just square the top and bottom on each of these. It's gonna kind of suck, but I mean, we have to do it. So let's take a look at the top. I'm gonna have to do e to the x plus e to the negative x times itself, right? E to the x plus e to the negative x. Then on the bottom, squaring the 2, that's just 4. Then over here, minus, I'm going to have to do e to the x minus e to the negative x. Same thing, e to the x minus e to the negative x, all over 4 again. Now, when you square this, the top, right, I wrote it out just to make sure no one, forgot that you have to actually expand that, FOIL it, right, this times this, this times this. So what do we get here when I do e to the x times e to the x? What's that? E to the x, you could say e to the x squared, but what is that? If you have something to a power, you multiply, so e to the 2x. So that's the same as e to the 2x. I prefer e to the 2x, so I'm going to write e to the 2x. Now I do this times this. So you multiply those, they have the same base, e, so you add the exponents. What's x plus negative x? 0. What's e to the 0? 1. So that's a 1, so plus 1. Now when I go and do the inner ones, don't I get the same exact thing? Right? E to the 0, that's 1. So plus 1. And then when I do the last multiplication right here, I get plus e to the negative 2x. All of this over 4. Minus. Now do the other one. E to the x times e to the x, e to the 2x. How about that next one? E to the x times negative e to the negative x. That'll be minus 1, minus 1. And then the inside one here, another minus 1. And then the last one here, so it'll be plus e to the negative 2x. Then all of that over 4. And since they both have the same denominator, can't you combine these two together? And I'll have to make sure I distribute this negative through, which means it'll change this one to a minus, this one to a plus, this one to a plus, and this one to a minus, right? That's what's going to happen. Which means that this e to the 2x minus e to 2x cancel, and the e to the negative 2x minus the e to the negative 2x cancel, and we get 1 plus 1 plus 1 plus 1, which is 4 on top, and 4 on the bottom, so you get 4 over 4 is 1. So that's the verification of that identity. Questions? Now that's just one of many identities that there are with the hyperbolics. Here are the ones that you should know exist. Not necessarily you need to know them and be able to regurgitate them, but you should know about them. Sine hyperbolic negative x is negative sine hyperbolic x. Cosine hyperbolic negative x is cosine hyperbolic x. This is the identity that we just did. This one, very similar to pre-cal. We had the Pythagorean identity, but we had 3 different versions of it. Here we have another version of this one. And then these are our sum formulas. Hyperbolic sine of a sum, angle sum. And then cosine, you have another one. Okay, I think I'm at the end of that page. Then I was supposed to talk about the derivative, sorry. And then we are supposed to find this derivative. So that's where we are. So if I take a look at y being defined to be x secant hyperbolic e to the x, and we're asked to find y prime. I just need to take derivative of that. So what am I going to use to take the derivative there? So there's going to be some chain rule for sure. There's also another rule happening right there. Product right there. You've got a product rule. The x times the hyperbolic secant. Oh, geez. So it'll be the derivative of x, which is 1, times the hyperbolic secant, which I'm not going to touch yet, plus now, finishing up with the product rule, derivative of secant hyperbolic of e to the x. Well, now we have to use chain rule on that, right? What's the derivative of secant hyperbolic of x? So we look on our thing if we don't remember, right? Cosine. No, wait. This secant is negative secant hyperbolic x, tangent hyperbolic x, isn't it? So, and it's negative. So I'm going to put here negative secant hyperbolic of e to the x, right? Because chain rule, I don't have x in there, I have e to the x in there. And now I'm finishing off that derivative, tangent hyperbolic e to the x. And now we have to say, that's just derivative of secant hyperbolic of what's in here, right? Then chain rule says derivative of what's in there is e to the x. So I have to tack that on to the end out here. And then finishing off the product rule, right? I need what? An x out there. So cleaning up, something like secant hyperbolic, and then we have minus x e to the x secant hyperbolic e to the x tangent hyperbolic e to the x. I think I've got it all there. And you might recognize you could also factor out a secant hyperbolic e to the x from both of those if you wanted to. It wouldn't be any more correct or less correct to do so. But that's probably something you might want to do if you were ever setting this derivative equal to 0, right? Factor out the secant hyperbolic e to the x. Questions? All we're really doing here is we're introducing some new functions and then practicing taking derivatives of them. All right, moving along. Do I need to leave that up there, or y'all just let me know if you need more time with something. I do post these, yes. All right, so just like we had before, right? We had our trig functions, then we had the inverse trig functions. Now we have these hyperbolic trig functions, and so it makes sense to have inverse hyperbolic trig functions. and here they are. All right? Just like with the inverse trig functions that we started with last class, we have to make proper domain restrictions in order for the inverses to exist. If you go back to where we were in the beginning, when I was showing you the pictures, look at this one. That's the hyperbolic sine. Does it look like a function that has an inverse? Yes, it looks like it passes both the vertical and horizontal line test. So that one we shouldn't have to worry too much about restrictions when we talk about its inverse. But when we look at cosine hyperbolic, absolutely that does not pass the horizontal line test. So there will be some domain restrictions there. And then that one looks okay, doesn't it? Vertical, horizontal. These are asymptotes, but we will have to restrict something because it is bounded. It appears to be bounded. All I'm getting at is, for that note, right? No. Right here, right? The inverse of the hyperbolic sine, we said we didn't have to worry about domain. But there are some restrictions here for the others. So there's actually 6 of them, but I'm only going to list 3 because we don't use these very often. And these are the 3 that we usually use if we're going to use them. Right? Those are the only 3 that we'll talk about. So here's our next example, is to show that hyperbolic inverse x is this. You ready? This is kind of fun. If you define fun to be anything related to what we're doing right now, then this is kind of fun. I want to show that the inverse hyperbolic sine x is equal to natural log x plus square root x squared plus 1. The purpose of me showing you this, all right, is not necessarily because I'm going to test you on doing this. It's really just to show you how it is that we approach things like this. Like, how is it that we go and try and show that that is true? Well, here's where I will start. I will start with what I know about hyperbolic, anything related to sine, and that is, I know that sine hyperbolic x is defined to be e to the x minus e to the negative x over 2. Do you agree? Yes? Everyone agree with that? That's the only thing you know, right? And you're trying to find the what the inverse of that function is. Anybody have any ideas? Cancellation property? So you're saying, like, take the arc sine on both sides? Yes? That's an option. I'm not saying I disagree with that. How about up there? Can we take inverse on the top one? Well, isn't that what I'm trying to show is true? So can you take sine on top one? That's what I'm trying to show is true, though, right? I can't touch that because that's what I'm trying to show is true. This is all I really know, right? How did we do this? I know what I'm pretty sure I know what you're saying because I was just about to show it. What I said, what did we do last time? We said, where is it? No, that was just when I was yapping. Here it was. we were trying to figure out what the derivative of something was, right? Isn't this what we did? But we wrote down what sine, we wrote down the relationship here, right? I think that's what you maybe are getting at. Okay. I'm just writing down ideas right now, all right? Rather than just showing you exactly how we do this. So we know that sine hyperbolic x equals y means that x equals sine hyperbolic inverse x. Is that what you were saying? Yes, okay. Oh, yeah. Then that's not what you were saying. That's what you were saying. Okay, I have that. I'll agree with that. But what does that do for me? Does that do anything? Okay, now what are we trying to show? Are we trying to show what a derivative is here? Or are we just trying to show what look, it's saying here, show that the inverse hyperbolic sine function is equal to this. I already put it up here, right? Here it is. This was given to us as a formula, right? Yes? Okay. So I'm not trying to find a derivative, so I'm kind of back off of derivative because that's not what I'm trying to show. All right. Let me go back to last class again. This was when we were doing derivative. Let's go back up further. That was the quiz. There was something we did in here. We had this also. We had reference triangles. We don't even have a triangle here, do we? Pardon me? Yeah, that's right. And it doesn't. Unfortunately, it doesn't apply. How in the world do we get that this is this from this right here? I mean, that's so. Let me try and take you back. I'll take you back to a course, another class. All right. Let's say that you were in like college algebra and somebody gave you y is equal to 3x. Oh. And they say, find the inverse. Or I should have said f of x is 3x. And I say, find the inverse. Remember how we find an inverse? You replace f of x with y, right? Then you switch the x and y variables, make this 3y, and then you solve for y, so you get x over 3, that's y, and then that's your inverse function. And it kind of makes sense. If you have a function that triples something, then to undo that, you need to divide by 3. But this was the technique. We looked at the function that we had in terms of x, we called it y. Then, because the inverse is supposed to take x back to y and y back to x, you know, right? It's supposed to undo it. We switched the x and y variables here. Then we solve for y. That's the standard technique for finding an inverse of a function. I'm going to do that exact same thing. Now, what is the function I'm trying to find the inverse of? This right here, right? That's what I'm trying to find the inverse of. So I'm going to call that y, and then I'm going to switch x and y, and I'm going to solve for y. And that's going to be kind of fun. The reason why I put this all down here is just to kind of get you to see that, you know, what are we being asked for? And then what are our ideas? Like, what are the things we know? Like, is this going to help us? Is that going to help us? Reference triangles. We have to kind of put it all out there and see what makes most sense. At the end of it all, though, we go back to the college algebra technique to do this. Anybody have a question on the technique I'm about to use? Let's see if it works. I'm going to take e to the x minus e to the negative x over 2. I'm going to switch the x and y, which you really don't have to do this, but if you're following what you did in college algebra, then that's what we're going to do. And now I'm going to solve for y. So how do I solve this for y? Ooh, I need to get y by itself, right? Okay, so let me clear the fraction. I'll multiply both sides by 2. When I multiply both sides by 2, I get 2 equals e to the negative y minus, e to the y minus e to the negative y. Wow. Well, you can take the natural log. You can't. Yeah, you could. What do y'all think about that? Take the natural log on both sides. Let's see what happens. Okay. I'm going to do it in a different color because I'm not quite sure if this is going to work or not. If I do that, my only concern with doing it like this is what am I going to do now on the right side? Can I do anything to this? The whole idea is to get the y by itself, right? Get the y by itself, right? Does this allow me to somehow get this y out of here? How? Okay, be careful. Be careful. Careful. Yep, I know it's all in there, but okay, here are the log properties. Natural log of u times natural log of v is natural log of u plus natural log of v. Natural log u divided by v is natural log u minus natural log v. Natural log u plus v does not have a formula. Or minus. It doesn't have a formula where you can break it down. So you cannot pass a natural log through. First of all, we can never call it distribution because this is not a number. This is a function. So we are doing natural log of something. This is its argument. The only formulas we have that make this a little nicer is if that's multiplication or division inside. If that's the case, we can split it. Do y'all see what I'm getting at here? That's why I said let's do it in blue, because I'm not quite sure if this is going to work. We cannot use the log yet to be able to pull the y out. Understand? So that's not going to work. So let me help guide you through it, all right? But that's a good exercise to go through that to see why that's not working. All right, so back to this. Back to this. Well, you know what? I don't like erasing stuff. I'll just go down here. I'm at 2x equals e to the y minus 1 over e to the y. Is that correct? Isn't that what that means? Okay. I'm going to multiply everything by e to the y, both sides of the equation. And part of the reason I'm showing you this is because I'm willing to bet nothing that there's very few of you who have seen what I'm about to do. I'm willing to bet quite a bit. If you have seen it, let me know, because I'd be somewhat surprised. I'm going to multiply everything by e to the y. So that's the left side by e to the y, right? And then this times e to the y would be what? E to the 2y. And then the other one would be what? Just e to the y over e to the y, so just 1? Now, you may argue, wait a minute, man, you just made this like just as ugly, right? Anybody know what I'm going to do? Okay, then let me give a little bit of guidance, because I really want to see if anyone's seen this, because if you haven't, it makes it worth coming to class, right? I mean, you're going to see something you haven't seen before. Does anybody realize that this is a quadratic equation? Look, I'm going to move everything to one side. So e to the 2y, I'm going to leave it on the right side. I'm bringing over 2x e to the y, and I still had a minus 1 over there equals 0. Okay, does everyone see this? Just move this term to the right side. Now let me write it just a little bit different. This is e to the y squared minus 2x e to the y minus 1 equals 0. Do you agree with that? Now, to help you see how this is quadratic, I'm going to do just a quick substitution. Everywhere I see an e to the y, I'm going to replace it with u. And I just need to remember that when I'm done with this, I need to switch back. Okay? So everywhere you see an e to the y, replace it with the u. And what do you get? U squared minus 2x u minus 1 equals 0. Now, is this a quadratic equation? I mean, honestly, you've always been taught that quadratic equations look like this, right? Ax squared plus bx plus c equals 0. And you've always been told that a, b, and c are just what? Constants, right? And that the thing being squared and the thing here, that's your variable. If that's the case, then what's the variable here? A u. What are the constants then? 1 and negative 2x. It's not a constant. And then over here, it is a constant. Do you see? A is 1, b is negative 2x, and c is negative 1. This is still, though, a quadratic equation. We say a quadratic in u, meaning that u is the variable. It's a quadratic in u, but the coefficients aren't constants. And you may or may not. How many of you have ever seen the quadratic equation or the quadratic equation solved using quadratic formula like I'm about to do, where you didn't have a, b, and c being constants? Anyone seen something like this before? Yes? Okay, good. That's a great thing. So I'm going to just solve this using quadratic formula. Quadratic formula says that my variable u will be equal to, now what's quadratic formula? Negative b plus or minus square root b squared minus 4ac all over 2a, that whole thing, right? Okay, so for us, though, in this problem, a is 1, right? B is negative 2x. C is what? Negative 1. Okay, I'm going to use A is 1, B is negative 2x. That's the thing in front of u, and then C is negative 1. So my quadratic formula is negative b. What's negative b? 2x. Plus or minus square root. What's b squared? 4x squared. Minus 4 times bc, or 4ac. Hold on, it's b squared minus 4ac. AC. So a times c, so negative 1. So this will be plus 4 in here. Got that? All over 2 times a, which is 2. Okay, let's clean this up. This is 2 plus or minus. What can come out of that root? Right, I can factor a 4 out of each of these, right? And then pull that out as a 2 in front of this square root. So that can become a 2 in front of the root. What's still under the root? X squared plus 1, and then all over 2. I have a 2 in all the terms, so I can cancel it. So here's where I am. I'm at the end of the page, so I have to move on to the next one. But does anyone have any questions on this? Next page, here it comes. I am at the point right now where u is equal to x plus or minus square root of x squared plus 1, right? But what was u? It was e to the y, wasn't it? And now, remember, we're trying to solve for y way back when. That's what we were trying to do. Now you can come in with natural log on both sides of this equation. And when I take the natural log of e to the y, I get what? Y. And when I take the natural log of the right side, I get natural log of whatever the right side is. Is that what I was trying to show? Is that what I was trying to show? There's a little bit of an issue. Where's the issue? Plus or minus, right? What was it that I was trying to show? That it was what? A plus or a minus? That it was a plus, right? Now, why is it that it has to be the plus and it can't be the minus? Somebody tell me about the relationship between these two things right here. Which one of these is a bigger number? Is x or the square root of x squared plus 1 bigger? X versus square root of x squared plus 1. Which one's always bigger? Well, look, yeah, let me take away, if I take away this 1, right? If that 1's gone, then what's the right side? They're basically equal, right? So if I add 1, it's a little bigger, isn't it? So if this one's always bigger than this one, if the one on the right's always bigger than this one, I can't have negative here. Why? Because then this minus this would be a negative, and I'm trying to take natural log of a negative number, and I can't do it. Does that make sense? So I chunked the negative because it's just not possible. Remember, whenever you solve a quadratic equation using the quadratic formula, you get two potential solutions. Potential solutions. It could be that one of them is extraneous, and we actually get that one of these formulas is extraneous. We can't use it. So throw it out. So we have verified that this is true. That's kind of neat, right? All right, so now let's get to a derivative. How would we show that the derivative of the hyperbolic inverse hyperbolic cosine function is that? So trying to show that the derivative with respect to x cosine hyperbolic inverse x equals 1 over square root x squared minus 1. Do I know what the hyperbolic cosine inverse function is? It's on your sheet, right? We just need to take derivative of this. That's all. So I'm really trying to take derivative of natural log x plus square root x squared minus 1. Do y'all see that? I'm just looking it up on the sheet. Cosine hyperbolic inverse. This right here is this. And now I get to take its derivative. So what is the derivative of natural log of a bunch of stuff? 1 over it. 1 over it. So 1 over all of that stuff inside. So 1 over x plus root x squared minus 1 times the derivative of what's in here, right? Derivative of what's in here. So derivative of what's in there, we have addition between two terms. So derivative first one is just 1 plus now the derivative of the second one, which is the derivative of the square root of x squared minus 1. That's a little bit of chain rule there. I'm going to do this one the other way because I've been using the 1/2. I'm going to do this instead for those other students who learned it this way. Okay, that's the derivative of the square root of x squared minus 1. It's 1 over 2 times the square root of x minus 1. Then times the derivative of what's in there. What's the derivative of what's in there? 2x. I think I've got some 2's canceling there. So I am at this point. 1 over x plus square root x squared minus 1 times 1 plus square root, or 1 over square root x squared minus 1. Where did I forget? Oh, I did forget the x. Thank you. That probably would have mattered, huh? Now what? Can I actually take this whole thing and distribute it like this? Yeah, I could, right? I could do this whole thing times 1 and then this whole thing times this. That's one way to do it, right? I could also slide this whole thing on top and then come in and try and simplify. So how about this? Because it's 10 after. I'd like for you to just finish that up on your own and on a separate piece of paper. Just start from the beginning, work it out, separate piece of paper. Not right now. Bring it and turn it in next class. All right? So all you're trying to do is get it up, algebraically mess with that and get it to that, right? That's what you're trying to do? All right, I'm going to move on. All right, the rest of the derivatives of the hyperbolic inverse trig stuff can be found in the book. And also on that formula, the formula sheets, right, that I was telling you about, they're all there. Here's the catenary that I was telling you about. Anytime you have a wire hanging, it has this format. So notice that you have an a, which is like a scalar, and then you're dividing the x by a. So those a's have to be the same in order for it to represent a wire, a hanging wire. And if you change the value of a and c, you can kind of see, you know, there's a wire. So if you hung a wire, it should look like that. I don't have anything. I don't know if my computer is, let's see, what can I use? Nobody has a wire, do they? I've got so many wires. This one's just, it's not flexible enough. Yeah, I don't have any shoelaces today. All right, so let's see. Yeah, that's not going to work. I've got so many wires hooked up to my computer that can you try that? Thank you. Let me see if this works. I don't even know if this is going to work. I've never tried this. What the heck? No, I'm just kidding. You're one of those people who leave it all knotted up, and I think this happens no matter what, right? No matter what. All right, I don't know. Who wants to hold the other side? I still don't think this is flexible enough. Let's see. Now we got this is all messing it up, right? All right, so let me try and change it a little bit. I don't know if you believe this or not, okay? But no, Do you understand? Like if I put a parabola up here, the parabola wouldn't, that's good. The parabola would not look as good as a fit as that does, because that is what it does. So that's right. Well, that arc length did change. Well, yeah, this picture is not holding the same, it's not keeping the arc length constant. So that's why we had to kind of change where we were when we were holding it. The point is that if you truly get a wire that's not quite as rigid as this and it's very flexible, is allowed to hang, then it should hang just right on top of this graph. Whereas if I put a parabola up here with it, the parabola will do something else. You just can't get a wire to hang to look like that parabola. Thank you. So if I was hanging something like this, right? And I want to kind of exaggerate this a little bit. Can we shut that? Do you mind just shutting that door? Anyone? Yeah. Those damn hygienic blow dryers are ridiculous. If I'm hanging this from some tower, right, and I have, you know, if this is like an electrical wire, we have some insulator, right, to keep it from going in contact with the pole itself. Insulator is usually made out of some like ceramic or glass or something. And so what you have there is where the wire comes in and connects to the ceramic, you actually have a force on that ceramic, right, pulling. And that force, the ceramic has to be able to withstand that force, right? So what you need to know is the direction. You need to know like the direction of that force, right? What's the direction of that force? So what you would do is you would just figure out what at that point, you just figure out what the slope of the tangent line is, right? And so the force at that point is actually in the direction of that tangent line, and it would be computed by being able to determine the weight of the wire, right? Which again would be another problem that you would have to figure out. But you'd be able to determine the force on that point and the exact direction of that force. And then you would say, is your ceramic insulator going to be able to withstand that force, right? What is it rated at? Things like that. But to do all that, to find your derivative and all that, you need to know the derivative of the hyperbolic cosine function, right? Which we have. We could figure it out. So I'm just trying to show you some usefulness of one of these inverse hyperbolic, or one of these hyperbolic functions. All right, there's the homework for this section. Was that on your handout? Yes, it was? Okay. All right, let's move into the next section. Everyone have it? I'm moving on. Up to this point, pretty much everything we've done is not a whole lot of Cal 2 in what we've done. So now we do it. We start to get into it. These notes were online, so these were available to you. You can print them out. It's not real long, and there's not a whole lot of stuff here. All right, so we're jumping to Chapter 4, Section 7, Antiderivatives. So no, antiderivatives. A function, capital F, is called an antiderivative of little f on some interval I if the derivative of capital F is little f for all x in the interval. If capital F is an antiderivative of little f, then capital F plus c is the most general antiderivative of little f. Here c is any constant. So we're going to try, before we get into what that definition meant, let's actually try and take a look at this in pictures. If f of x is 2x, little f is 2x, right? Then capital F of x is x squared plus c. That's what we call the general antiderivative of little f. Now the reason why it's called the antiderivative is because if I take the derivative of this, don't I get this, right? So we're looking in Cal 1, we took derivatives. With antiderivatives, we're trying to go backwards. We're going to say, okay, we're looking at something saying, hey, that came from where? We took a derivative of what to get this? So to get this, we had to take derivative of that, plus any number. So here's the picture that goes along with this. What is this right here, this red one? That's 2x, right? That's a line, that's 2x. This is the exact problem right here. This is 2x. And we just said that x squared, right, plus any number is its antiderivative. But we said it could be x squared, or it could be x squared plus 1, x squared plus 2. So I could move that. That's still x squared plus 5.5. If I take the derivative of that, I still get this, right? So what we actually get is not, when you take the antiderivative of a function, there's not just one answer, there's a bunch. There's actually infinitely many. So you get what we call like the family of antiderivatives. I mean, all of these are antiderivatives. Right. Here's a few of them. I could fill that in where it's completely black because there are infinitely many. So what if we have this? We have a quadratic this time, right? And I'm trying to find an antiderivative of that. So this came from what? So we go backwards. And do you just agree that it's this? I mean, we're going to spend time on how do we get backwards. But do you agree that if I take derivative of capital F, I do get little f, right? You just do a bunch of power rules on that, right? Derivative of that last constant is 0. So for that one, the picture would be, here's the parabola, right? We said the antiderivative of that was this cubic function. But not just that cubic function, it could be that one or any of these, right? So we have some family of cubic functions. Any of those could be antiderivatives. Now, you do want to look at page 249. Can someone confirm with me who might have their book that that is the correct page number? I'm pretty positive it is. Page 249 should have a table on it, and it has common antiderivatives. These are also in your formula sheets. How many of you brought your formula sheets? Okay, I would go ahead and just have those all the time because it's a good reference. So we are going to find the antiderivatives of these, and then we're going to finish. That's all I'm going to do today is just example 1, and that's it. And I might just do A and B. Let's just see how this goes. So what if we have to switch back. All right. This is little f, right? We're trying to find the capital F. We're trying to figure out what we have to take derivative of to get this. So how do we do this? How many of you learned some antiderivative stuff already? Let's see, show of hands, see where people are, okay? So like power rule, there's a power rule for it. All right, I'm gonna give you the power rule now, and we'll spend next class, we'll spend more time on it. But let's try and come up with the rule ourselves. Let's say that I have, let's say that little f of x is x to some power. Underneath this, I'll put an example, x cubed. What do I have to take the derivative of to get x cubed? What do we know about the power of what I have to take the derivative of? It's x to the fourth, right? Because this comes from, has to come from an x to the fourth because the power comes down when we take derivatives, right? So I already know that this, when I go to try and find capital F, right, I'm trying to find capital F over here. I know capital F will at least be an x to the fourth, right? But see, that doesn't work, does it? Because if I take derivative of this, the 4 comes out, right? So I don't want that 4 to be there. So how could I get rid of the 4? I just put a 1/4 in front of it, right? And now when I take derivative, the 4 comes out, it gets canceled out by the 1/4, and that would leave me with the x cubed. So up here, in a more general format, I know that the n here had to come from something 1 power higher. So couldn't I say it comes from n plus 1, right? But I need to make sure that when I take derivative, that power comes out, so I need to kill it. So I put out in front of it 1 over n plus 1. Does that make sense? Now, we also have to say, look, you could always have had any constant out there, right? Because the derivative of any constant would be 0, so that would go away. Now, there is one case that this formula doesn't work. Think about it right here. Right here. When would this not work? If n was -1. So I'm going to put next to this only works if n is not -1. And I'm going to just squeeze some room in underneath this. So what would happen if n was -1? This formula wouldn't work, right? But come back here and tell me what this function is if n is -1. What's x to the -1? It's 1 over x. Do you know what you take the derivative of to get 1 over x? Natural log, right? The natural log. So this one comes from natural log x plus some constant. That's what you do if n is equal to -1. What we have here is what's called the power rule for antiderivatives. If you have a little f that is some x to some power, then to find the general antiderivative, you use this formula as long as the n is not -1. If the n is -1, then it's just natural log. Let's just do this one, all right? And then we're going to call it not a complete day, but we're not going to go through any more notes. All right, so if I'm trying to do that, because we have 1, 2, 3 separate terms, right? Terms of separate addition and subtraction. Just like with derivatives, when you're going backwards, you can do each term one by one. So how about that 2/3 x? 2/3 x cubed. I think I'll do that as its own problem here. If I'm trying to go backwards here to figure out what capital F that came from, what can I say about the constant in front? Do you remember what happened when you were taking derivative? If you had a constant out front, didn't that constant just come with it? Right? So when I try and go and take this back to the capital F, I can just tack the 2/3 onto the front. Just put it there. And then I just figure out what the antiderivative of that is. So forget the 2/3 is here, and now use that formula. What did we say the antiderivative of x to the third was? x to the fourth with the 1/4 out in front, right? So we have 1/4 x to the fourth. That's not 4, that's an n. There, like that. Now just clean up the fraction in front. That's really just 1/6 x to the fourth. How do you check your answer? Take the derivative, right? Take derivative of this. 4 comes out. What's 4 over 6? 2/3, and then the power came down by 1. Yes? Yes. What I'm going to do is I'm going to add the plus c when we're finished with the problem, because this was just the first term. Okay? So I'm working this kind of piece by piece right now. I'll come back and grab this later and put it in my answer. Now let's look at the next one. I have plus 4 square root of x, so I'll do that one. I'm going to do it on the next page. 4 square root of x. Well, before I can even use a rule, right, I need to rewrite x as a power. So this is same as 4x to the 1/2, right? That's what it means to be square root, right? Now let me go backwards. Try and find my capital F. What do I do with that 4 in front? Just bring it along, right? So I'm just going to bring that 4 out, include it in my answer, then times now x to the 1/2. So things are maybe a little bit tricky. Let's slow it down. We said we'd always take the x and we would add 1 to the power, wouldn't we? So I'm going to take 1/2 and I'm going to add 1 to that. And then in front of it, I always divide through, right? I always put 1 over. I divide through by whatever this is, right? So I'm just going to put 1/2 plus 1. Do y'all see that? This before it was 3 plus 1, so it was 4. Then out here was 3 plus 1, so it was 4. Here, because it's a fraction, might require a little more thought. 1/2 plus 1, 3/2. So right now, here's where we are. We've got 4, got 1 over 3/2, x to the 3/2. But 1 divided by a fraction is the same as the reciprocal, so that's really a 2/3. So 4 times 2/3 x to the 3/2. And if I do 4 times 2/3, I get 8/3 x to the 3/2. And we can always check it, right? Check. 24/6 when we take derivative, right? Comes out 24 over 6 is 4. And then when you take 1 away from 3/2, you get 1/2. So it works. And we go for the last one. I have negative x root x. Let me just do the x root x. I won't worry about the negative. X root x. First thing I do is I rewrite that as x times x to the 1/2, which is x to the, you add the powers, right? X is x to the 1, so add these, x to the 3 over 2. And now we apply the power rule to this. So we go backwards, capital F. I'm always going to have 1 over something, x to the something. So what is it that I'm raising this one to? 5 over 2. So you're doing 3/2 plus 1, right? And 3/2 plus 1. 3/2 plus 1 is 5/2. So this is 2 over 5 then, x to the 5 over 2. The goal at some point is for you to be able to go from this to this without writing a single thing down and doing it all in your head. That's the goal, to do all the fraction stuff in your head. And if you're already there, then good. If you're not, it's just going to take some practice and starting to see the pattern. And all right, so what is the final answer to this thing? Let me get back up here. Our final answer, I don't have a whole lot of room to stick it in right there, but here we go. Capital F of x was, that first one was 1/6 x to the 4th. And then, what was that? I thought it was 6. what was this one? 8/3 x to the 3 halves, and then minus, because it was negative there, 2/5 x to the 5 halves, plus c. The great thing about antiderivatives, you can always check, right? As long as you can take a derivative. All right. Attendance sheet needs to go around, and I'll start it here this time. Next time I'll start it there. We did not do attendance on Tuesday, so please sign in for both days, assuming you were here on Tuesday. There you go. I don't think I have anything else on this. I'm not going to give you any homework from 4.7 at this point. Do you have any questions?